It's on. Okay. Yeah, so hi everyone. I'm going to talk a little bit about denoising. I think this is the session about video editing. This is actually not about video editing, but about image editing, probably. So I'm at the Max Planck Institute for Biological Cybernetics. Actually, if you Google this, maybe you will not find it, and that is because it doesn't exist anymore. Now it's called the Max Planck Institute for Intelligent Systems. I guess it's some rebranding or I don't know. Yeah. So since I'm going to talk about denoising, let me first say something about what denoising is. And I think we can regard it as being a decomposition problem, where what you're given is a noisy observation Y of an image, but it's really the sum of two different things. It's the image you want to observe, X, and some noise, N. And the problem is to decompose Y into these two components in a way that makes sense, makes you happy, so that you recover the true image as best possible. So this is an impossible problem. There's no way you can solve it unless you assume something about what images are, how they look like, and something about the noise. Ideally, you should really assume something about both the images and the noise. Furthermore, we could divide denoising algorithm into two broad categories where really almost all denoising algorithms fit into the first category, where you make sophisticated assumptions about images because, well, images are complicated, right? When you think about natural images, images of scenes that could happen every day, you can do a lot of statistics on that. But people usually assume that the noise that corrupts these images is relatively simple. Additive, white, Gaussian, zero mean, same variance for every pixel. We'll see that this actually does not hold for real cameras. So I would introduce a second category of denoising algorithms that makes fewer assumptions about images, maybe because you cannot or you don't want to, but you make more sophisticated assumptions about the noise. So I was saying that we're going to denoise astronomical images. This is not an astronomical image. Actually, yeah, it's a natural image or a scene of something you might see every day. I live in Germany, so this is not something that I would see very commonly, but if you go hiking in the US, I think you can see something like that. It's a color image taken from the Berkeley segmentation data set, and when people denoise images, they often take pictures from this data set as a reference. To make things even simpler, people usually take black and white images, like this image, for example, which is called Barbara. It's a very common image for image denoising. Now, my point is that astronomical images look different. This is an image of the Horsehead Nebula. This is a globular cluster. I think it's M13, and I think it's a very typical astronomical image in the sense that there is relatively little structure. There's a lot of dark background and stars. And this is very different from natural images. And this, well, this is a picture of a meteor shower. You can see these streaks, which are just meteors passing. So this already tells you that maybe these images are long exposure photographs, which is also different from natural images. So to sum things up, well, most denoising algorithms fit into this left column, where you make strong assumptions about images and weak assumptions about the noise. So people have used all kinds of things. Maybe you know about fields of experts. It's a global image prior trained on a data set, like for example this Berkeley segmentation data set, and you learn a bunch of filters which are very convenient for denoising natural images. This is maybe something you would not be able to do on images which contain very little structure. BLS GSM is a very successful wavelet denoising method, which also makes assumptions which will not necessarily hold in astronomical images. And the list goes on and on and on. There's a very good denoising algorithm called BM3D. I'll mention it briefly later on. And so what we're going to talk about is denoising astronomical images, and we're going to make very few assumptions about images, but we're going to learn more about the noise that corrupts these images. Our assumption is that the noise is not as simple as what people usually assume it to be when they denoise images. And so our hypothesis is that by exploiting this, we can somehow create a better denoising algorithm for astronomical images. I mentioned that astronomical images are usually taken with a long exposure time. and actually also usually very high ISO values, which just means that the amplifier is very high, and this just creates noise. And the typical noise that is created in this way is so-called dark current noise. Dark current noise is noise that is created by thermal electrons. Just because the sensor of the camera is warm, electrons get freed from somewhere and fall into the pits, and the camera cannot differentiate between the electrons that were created thermally and the ones that were created by photons, the ones that you are actually interested in. So because this happens even in the absence of light, just in the presence of heat, it is called dark current. And so our claim is, and I will show this, is that dark current is not as simple as the noise that people usually use to corrupt images. However, it is simple in the way that it is assumed to be additive to the image. You can just assume that electrons from photons fall into a pit, and electrons that are thermally generated also accumulate in the same pit, so we can assume it's additive. And this assumption works. So most denoising algorithms currently in existence are not designed to handle that kind of noise. So to summarize, we're still interested in the denoising problem. We have a noisy observation, and we want to decompose it into a true image and the noise that corrupted this true image. But this noise now, we know it comes from dark current. And actually, there's a way to sample this noise by simply putting a cap or a lid in front of your camera so that absolutely no light will enter your camera, and taking a picture, you record only the dark current, right? Because it happens even in the absence of light. So a picture like that, which you take without any light at all, is called a dark frame. And a dark frame is a sample from the dark current distribution. So this is how we're going to learn about the noise. We did this with a camera which we can cool, and we recorded 200 dark frames for a bunch of different settings: 10 degrees Celsius, 5 degrees Celsius, 0 degrees Celsius, and minus 25 degrees Celsius. And here we are plotting two different things: the mean pixel value and the variance of these pixels. We chose 1,000 random pixels, and in the very top left corner of this slide, we sort these pixels according to their mean value. And what you can see is that not all pixels are identical. In fact, some have a very low mean, others, you can see they're spending upward, they have a very high mean. And when you look at the corresponding variance, same sorting, you can see that those that have a small mean also have a small variance, whereas those that have a high mean also have a high variance. And what you can observe is that as you go this way, the temperature goes down, the noise goes down. The mean goes down, but the variance also goes down. So that's very interesting. What it tells you is that if you want to take an image that has very low noise, you can just cool your camera. So problem solved, unless, of course, you cannot cool your camera. So when you see things like that, well, the mean seems to correspond to the variance. And it's also, I mean, it's this physical system where electrons arrive somewhere. You immediately think, well, okay, it just has to be Poisson distributed somehow. You can imagine that each pixel has some rate lambda, which tells how quickly electrons arrive there, and might be modified by the temperature T. And so that might be somehow Poisson distributed, and then it's scaled with a factor alpha to arrive at a pixel value. And then it's very easy to estimate the expected value and the variance of such a pixel if you make these assumptions. And then you arrive at this very simple formula where you can have a single scalar alpha, which is given by dividing the variance of a pixel by its mean value. And so this didn't work. We tried this, and it just did not fit. We had a completely different alpha for every different pixel. So we're not exactly sure why this is the case, but in any event, this Poisson assumption does not hold. So maybe this is not so bad. Maybe we can just assume that each pixel has a Gaussian distribution. And now we're going to model each pixel in a sensor with a pixel-specific mean value, mu I, and a pixel-specific standard deviation, sigma I. And so we can write down the log likelihood of a noisy image given the true image, if we have these mu's and sigmas, which we estimated by recording a lot of dark frames. And this gives us a simple method to denoise images. We call it DFML, like dark frames maximum likelihood. You can just remove the mean dark frame and this will denoise your image. This is maybe trivial and you want to do better. Because if you remove the mean dark frame, it is likely that your image will still look grainy, which you do not want. You can maybe make an assumption that your image is supposed to look smooth. If you take a picture of the sky, you do not expect it to look grainy. It should be smooth. So a lot of what people do in astronomical image denoising is they usually assume that the image is smooth. And this is what we're doing here as well. We're putting a prior on the pixels, where we just look at one pixel and its neighbors, pixel xi and xj, and say that this sum is supposed to be small. If we combine these two models, what we have here comes from removing the mean dark frame, and this is our image prior given, which comes from here. Lambda is a hyperparameter. It has to be tuned. We set it to 100, and that worked well for all our experiments. And now, actually, this gives us a very simple algorithm to denoise astronomical images. You can just minimize this with gradient descent steps. We call it dark frame maximum a posteriori, where P is also a hyperparameter, which goes here, which we can set arbitrarily. There is a competing method, another denoising algorithm, which I would say belongs to the same category as ours, in the sense that it's designed to denoise astronomical images. It's by Gomez-Rodriguez et al., and it was submitted to ICCP. And it also works by using a library of dark frames like ours, but it works a little bit differently. It chooses dark frames from this library in a way such that it makes the image look as smooth as possible on a certain number of pixels in an image. And so because this process involves solving a quadratic programming problem, we called it QP. So we ran a bunch of experiments. This was taken with the same camera, which we can cool. So what you see on the top right is an image. Maybe I'll turn off the lights. Maybe you'll see a little bit more. A noisy image taken with that camera. And so it's really noisy, right? It's hard to see anything at all. And so we were able to record a ground truth image, or an image with very little noise, by just cooling this camera and removing cold dark frames. So this really contains very little noise, and this is what the image that you see on the top right is supposed to look like. Very smooth, and you can see a lot of stars, or just bright points, which are very difficult to discern on the top right. Usually humans can see very well past the noise, but in this case it's difficult because the noise just has a lot of structure. We ran a very good denoising algorithm, which is designed for natural images, BM3D, on the noisy image, by just assuming that the noise has the same variance for each pixel. And this is what came out, bottom left. Complete garbage. It's completely screwed up. Whereas our result is on the bottom right. Looks much better. So what this really means is that a lot of denoising algorithms are not fit for denoising astronomical images. So we tried a bunch of other denoising algorithms. For example, BLS-GSM is a very good denoising algorithm based on wavelets, and it was also not very good for this purpose. And you can see that going down, we get better and better results, and our method with a p-value of 1.4 achieved the best results on that data set. Okay, so this might be a little bit artificial. So what we did is we looked at real astronomical images. So this is an image of the Milky Way. This thing which you can see in the middle of the image is the Milky Way. And what you see at the bottom here is just, what is it? It's grass, and I think it's a sea, and there are some clouds here. And these insets are just magnified on the sides. So what you can see here, maybe, I'll magnify it later on, is that there are some so-called hot pixels. Here are these green things. There are no green stars, so if you see green pixels, there's something wrong. It's very likely to be noise. What you can also see, maybe you're sitting too far away, and actually it's better to look at this on paper, is that the image looks pretty grainy, and you don't want that. So we ran this algorithm by Gomez-Rodriguez, QP, on the noisy image. And what we observed is that the hot spots, the green pixels, disappeared, which is a good sign because those were clearly wrong, so it denoised. However, the image still looks pretty grainy, which is not good. That shouldn't be the case. With our algorithm, there are no hot spots, and the image does look pretty smooth. So what you could say, obviously, is that maybe we just smoothed the image. Maybe we just did a lot of simple things like erasing stars and just make the image look smooth, but actually destroyed it. And I would argue that this is not the case. If we magnify into these blue and red insets and look at the noisy image, again, you can see these hotspots. I hope everyone can see them now, on the right side especially, and you can see that everything is very grainy here as well. It's very grainy. And now the QP method, again, the hotspots are gone, but it's still very grainy. And now with our method, you can see that this looks very smooth. But did we remove stars? And in my opinion, we did not, because if we look at this image, you can see this is supposed to be grass, clouds, and well, the rest is sky. You can see that all of this is grainy. There are no stars that are supposed to show up here. So what looks grainy here are not stars. And same thing here. There's a lot of graininess which is not due to stars. It's actually due to noise. And here you can really, well, you cannot really, but on paper you can really discern between the grass, the clouds, and the sky. We did this for other images. This is the part of the Orion Nebula, noisy image. This is a wavelet method, the QP again. And again, our method looks very smooth. So this brings me to the conclusion. I would argue that a lot of denoising algorithms are not designed to denoise astronomical images. You actually have to do something different from what people usually do to denoise astronomical images. This is due to the fact that the noise is very different. And we have shown that using a pixel-specific noise model helps in achieving that goal. And that's it. That concludes my talk.
We have plenty of time for questions. Yeah. The blooming effects that you saw, how did you get structural?
So we did not observe blooming. This is, but you're right. It yeah, should be taken into account. But we never observed blooming. I'm not sure. Is this actually? Does this happen for both CMOS and CCD cameras? Yeah. Yeah, definitely it will happen for CCD cameras. I'm not sure for CMOS. We never observed it. Maybe we didn't expose long enough. If you overexpose, you will observe it, I guess, yes. Yeah. Yes?
Are there correlations between pixels and dark current fields? Truly independent?
So, yeah, they're truly independent. No. But okay, they are all dependent on the temperature of the chip. So to that extent, yes. Yeah.
I have a question. In the results you showed, did you do this processing after demosaicing of your images, or?
No. So we first denoised and then demosaicing and then gamma correcting. And actually, when I showed this image prior, what I should have said is that we don't look at neighboring pixels, but at neighboring pixels on the same color channel.
Okay.
Because yeah, otherwise it would have been wrong. Yes.
Yeah, because I was going to ask that if there was an effect on if the demosaicing affected the sort of visual appearance of the dark current. So.
Oh yeah. There's actually a very good tool for doing demosaicing and gamma correcting, which is called DC raw, which can. Yes.
Do you have to measure the dark current at the same temperature that you're shooting your images at?
Yes. So actually, this is a limitation of our approach, and that is we assume that the temperature setting is the same for the noisy image as for the dark frames. Yeah, this might be a problem for amateur astronomers, for example. However, we could use our method in combination with the method proposed by Gomez Rodriguez, because his method picks some dark frames from a library which tend to actually have been recorded at the same setting as the noisy image. So this is quite smart. So we could use this as a pre-computing step to figure out the temperature of the image or something like that. Yes?
So one thing based on the previous question itself, so you mentioned astronomical images are mostly long exposure images. So even if you start off with a cold camera, you're going to increase your temperature as you keep on exposing more. So which means your dark current is not at a particular temperature, but it's kind of an integration over temperature. So how do you account for that factor?
Yeah, we don't. Yeah, I guess you're completely right. Yeah. Yeah, it's hard to say. I mean, this also depends on the ambient temperature and other things like that. It's probably very difficult to take that into account. So, but maybe this is close enough. Maybe your camera does not heat up by more than 5 degrees Celsius while you're recording, and maybe that's okay in that case.
Just one more quick point.
Who's this one with the integration time and camera time to be used for this?
So for these, oops, I went in the wrong direction. For these 60 seconds, and for those 120 seconds, which is fairly typical for amateur astronomical photography.
On the camera? What camera time?
The exposure time?
No, what camera did you use?
Oh, it's a Canon EOS 5D.
Okay.
For both. Yeah. Yes. Oh, you said.
Okay.
Yeah.
I'll just do one last
A lot of digital SLRs, you go to exposures have a mode where they'll take a dark image that has the same exposure to do some basic dark current compression. The only reason you can do the same thing is get the dark current, get the reference dark current image right and take the other.
You mean that this could be incorporated into a camera as a basic?
Yeah, but just take the data, you get the results.
Oh, yes, maybe. Yeah, it's kind of hard to manipulate the firmware of these cameras, so but yeah.
Okay, let's thank our speakers.